Good morning, everybody, and thank you, Ram, for the introduction. So now, generally, I prefer a minimal black and white aesthetic for my slides. But the crew here at the Film Eye Museum gave me a gentle warning. They said, if you go with the slides, with white slides, you are going to blind the audience. So for Systems Distributed 25, we're going dark mode. All right, but of course, this is not the only meaningful transformation we are going to discuss today. So 2 years ago, to the month, in June 2023, I co-founded Resonate with one mission. And that is to solve complex problems with simple code. So we can focus on creating value instead of losing our sleeps, our minds, or our collective's will to live. So in other words, we can rest in peace. So, okay, complex problems, simple code. That's bold, that's catchy, and that is a sentence that looks good on a landing page, on a slide, and on a t-shirt. But there's meaning behind the marketing. So in this talk, we are going to explore 3 key questions. What is the source of irreducible complexity in our problem space in distributed systems? What is a source of accidental complexity in the solution space? And how can we eliminate accidental complexity to transform the complex into the simple? In other words, how can we eliminate the unnecessary so that the necessary may speak? Now, modern applications are distributed applications. Why? As Hannes told us, because otherwise it doesn't scale. Sorry, I couldn't resist on that one. But no matter the reason, modern applications are distributed applications. And a distributed application is a collection of concurrent components that communicate by exchanging messages over a network. And distributed applications are complex. That is, regardless of the programming language, regardless of the libraries, regardless of frameworks, or regardless of a platform we use. But why? Why are distributed systems complex? We can trace the complexity of distributed applications back to the defining characteristics of concurrency and of distribution. Now, we want to build an intuition, right? And we want to build an intuition about concurrency and about distribution with a minimal model of computation. So let's just define a system as a collection of processes and a process as a sequence of steps. Nothing more. And our entire system, our entire world consists of 2 processes, P and Q, and each process consists of 3 steps. The defining characteristic of concurrency is a non-deterministic partial order. In a concurrent system, we do not know what will happen next. In other words, the system randomly chooses which process will take a step next. The defining characteristic of distribution is non-deterministic partial failure. In a distributed system, we do not know what will fail next. So in other words, the system randomly chooses which process to simply discard. The concurrent composition, the set of all possible schedules of P and Q, leads to 20 distinct possible executions. The concurrent and distributed composition of P and Q leads to 69 distinct possible executions. Right? So now imagine the behavior space of complex distributed applications that consists of dozens of processes and each with dozens or hundreds of steps, executing in an environment with complex failure models ranging from process failures to network failures. Right? That's not a few dozen schedules, that's not a few hundred, that's not a few thousand, that is millions over millions of possible schedules. So without being overly dramatic, now we can safely conclude that concurrent and distributed systems are characterized by chaos. So, we need to survive in a chaotic environment, simultaneously confronted with non-deterministic partial order and non-deterministic partial failure. What's our best shot? Well, to find inspiration, we turn to the post-apocalyptic action and comedy movie Zombieland. And there the main character Columbus, played by Jesse Eisenberg, attributes his survival in a world overrun by the undead to a list of rules. The first rule: cardio. This is generally good advice, but unfortunately, and to our regret, we cannot outrun our problems. Which brings us to the second rule: double tap. And to quote the movie, to ensure that the undead are really dead, don't get stingy, hit them twice. So, we are going to confront non-deterministic partial order with coordination. Coordination refers to any mechanism that constrains the possible schedules to the desired schedules. So coordination ensures order. And the core of coordination is to wait. It's not communication. You may think that the core of coordination is communication. It is not. The coordination is fundamentally about waiting. We often use communication to communicate about when we should wait. But the fundamental mechanism is waiting. And then, second tap, we confront non-deterministic partial failure with recovery. And recovery refers to any mechanism that repairs broken schedules. Right? So recovery ensures completeness. And the core mechanic of recovery is to retry. Any component, any part of the system, or the entire system may abruptly terminate. Your only chance at progress is to start the component again. All right. So we have identified our survival strategies in a concurrent and distributed world: coordination and recovery. How do we implement coordination and recovery? To make our lives simpler and not accidentally more complex. Now this time we will not turn to a Hollywood blockbuster, we will turn to the history of software engineering itself for some inspiration. There were two major transitions in software engineering: the transition from sequential to concurrent programming, and then from concurrent to distributed programming. Initially, developers were tasked to write code for single machine, single core platforms. Platforms that are capable of performing one step at a time. And this era gave rise to the quintessential programming model, the sequential programming model. The sequential programming model is based on functions. And functions are the universal abstraction for computation, and they compose recursively. Even our largest systems are built from the smallest building blocks. Functions call other functions, call other functions in a simple linear flow of control. Functions are understandable. Functions are dependable. Functions enable us to think about the problem we want to solve. They do not force us to think about them. However, eventually developers were tasked to write code for single machine multi-core platforms. Platforms that are capable of performing multiple steps at a time. And this shift from single core to multi-core platforms necessitates a shift from sequential programming to concurrent programming. Now, what is the initial solution? The initial solution was to add threads. But unfortunately, adding threads to the sequential programming model is not simply a minor addition, it's a major disruption. In the paper, The Problem with Threads, Edward Lee argues that threads discard the most essential and appealing properties of sequential computation: understandability, predictability, determinism. Instead, threads are wildly non-deterministic. And the task of the software developer becomes one of pruning back that non-determinism. However, and to continue the metaphor, pruning a wild mass of brambles does not necessarily yield a pretty hedge. So then the author states that rather than removing non-determinism where not wanted, we should only introduce non-determinism where needed. So in effect and essentially, Edward Lee advocates for concurrent programming models. Programming models where concurrency and coordination are first-class citizens, not just bolted on. And my favorite programming model or concurrent programming model is async await. Because async await extends functions with promises. Functions I already understand, and promises are the universal abstraction for coordination. And async await has become the foundation of many languages such as TypeScript, JavaScript, Python, Rust, F#, C#, Kotlin. I probably forgot a few. Now, however, today, developers, for better or worse, are tasked to write code for multiple machines. And this shift from single machine multi-core to multi-machines necessitates a shift from concurrent programming to distributed programming. And the initial solution? Adding networking. Or to sound more elegant, to sound more principled, adding remote procedure calls. But unfortunately, just like before, adding networking to the concurrent programming model is not simply a minor addition, but just like before, it's a major disruption. In the paper Note on Distributed Computing, Jim Waldo and his co-authors argue that there are fundamental differences between the interactions of distributed objects and the interaction of non-distributed objects. And any attempt to hide the differences between local and remote procedure calls is doomed to fail. Distributed systems are different. And so, in effect and essentially, Jim Waldo advocates for a distributed programming model. Programming models where distribution and recovery are first-class citizens and not just bolted on. So now we can actually accurately and concisely articulate the meaning behind the marketing. Solving complex problems with simple code just refers to a language-integrated programming model for concurrent distributed applications. So that's a programming model that supports local coordination, global coordination, and recovery natively as part of the programming model itself. Now, to turn this idea into reality at Resonate, we have been working on distributed async await and the distributed event loop. So distributed async await contains everything you need to write your application, while the distributed event loop contains everything you need to execute your application. So we can think of distributed async await a bit as the interface and distributed event loop as the implementation. The programming model is a bit of programming language theory, and the execution model is a bit of distributed systems theory and distributed protocols. So I think especially for this audience, I hope there's a bit for everybody in here. Let's have a look at the interface, the programming model. A programming model defines a set of abstractions and the operations available to you to express your application. Like the classic async await, distributed async await builds on just two abstractions, functions and promises. Except in distributed async await, functions and promises are durable. So async await introduces promises as a primitive for local coordination. A promise is a synchronization barrier. Right? One function can await the completion of another function. Distributed async await introduces durable promises. And a durable promise has a unique ID, essentially a URL, and persists its state in durable storage. And consequently, a durable promise is no longer bound to a single process. So that makes durable promises a foundation not just for local coordination, but for global coordination and recovery. How? Like classic promises, durable promises synchronize within a process. But unlike classic promises, durable promises also synchronize across processes. And uniquely, durable promises act as a memoization barrier. On failure and retry, just reuse the value of the durable promise instead of re-executing the associated function. And that's it. There's like no complex libraries, no complex frameworks, no complex platforms, no workflows, no actions, no activities. There's just functions and promises. Right? So this simple concept is the very foundation of concurrent and distributed programming. As the name implies, distributed async await is an extension of async await, which is in turn an extension of sequential programming. So we just peel back the onion in a reverse way. We start with the sequential programming model and explore the extension to async await and distributed async await step by step. So in the sequential programming model, there's one interaction, a synchronous function call. When the caller invokes the callee, the caller suspends until the callee completes. And then the caller resumes with the return value of the callee. Function call. There's exactly one running function, the very definition of sequential. In async await, there are two interactions. An async function call and an await. So when the caller invokes a callee, the caller does not immediately suspend, but resumes with a promise representing the callee. Only when the caller requires a return value, the caller awaits a promise. And now the caller suspends until the callee completes, if it has not completed yet. So now, since the caller does not suspend immediately, there are now two running functions, or at least two runnable functions. And that's the very definition of concurrent. Now, in distributed async await, there are like 2.5. There's like 2.5 interactions. A local async function call, a remote async function call, and an await. Both local and remote async function call spawn an execution of the callee and yield a durable promise. The caller deterministically generates a hierarchical ID for the callee, encoding the callee's position in the call graph. Deterministic ID generation here is necessary to guarantee that every execution has an identity regardless of process failures and retries. A local async function call has pretty much the same semantics as a traditional async function call in traditional async await, but with one twist. On retry, since the ID is deterministic, if the callee already completed, the caller can simply reuse the return value of the callee without actually invoking the callee again. Now, however, a remote function call spawns an execution of the caller potentially on a different process, on a different node than the caller. So in a remote async call, the runtime creates a durable promise, but does not immediately spawn the execution of the callee directly. Instead, the runtime adds a tag to the durable promise, marking it as a remote invocation, and encodes the function and the arguments it wants to call as parameters to the promise. And then the distributed event loop will schedule the function to execute on a different node later. In either case, awaiting the promise suspends the caller until the callee completes. So that's our programming model. And we have two operations, invoke and await. And that powers the entire notion of distributed async await. So now that we have the facilities to write the code, next we need something to run the code. How do we run the code? What makes this code tick? That's right, computers. However, if the question is what makes it tick, there is always only one answer. Exactly, it's the event loop. The answer is always the event loop. In a local system, it's a local event loop. And in a distributed system, it's a distributed event loop. So we have to implement two pairs of operations, invoking and awaiting a local function and invoking and awaiting a remote function. Invoking and awaiting a local function is straightforward. Async await already did that. So locally durable async await unfolds like the classic async await, except that the invocation creates a durable promise and it skips on retry if it's already completed. Fairly straightforward. Invoking and awaiting a remote function requires a little bit more thought. And this is where we transition from programming languages to distributed systems and, of course, distributed protocols. So from here on out, in essence, what we are going to design is an async remote procedure call. All right. So invoking a remote function is still the simple part, because there's like really one very simple universal pattern. If in a non-distributed system I call a function, in a distributed system I send a message. And that's basically the function calls of distributed systems. So when we invoke a remote function, we create a durable promise, and we send a message to trigger its execution. That's cool. But awaiting the resulting execution, awaiting the response, sending the request, easy. Awaiting the response, that's the hard part. Awaiting delineates a computation in its past, present, and future. And the future is known as a continuation, the rest of the computation that must be executed after suspension on resumption. The continuation is the challenge. The continuation drags us down. The continuation is stateful. There's some stack, there's some heap, there's a process. And then there is a nail in our coffin. There's a TCP connection. None of that, exactly. None of that is desirable in a distributed system. On the contrary, continuations are a liability. That liability compounds with every invoke and await. That continuation is in memory, tying this execution and all that follow to the fate of the process they started on. And the deeper the call graph, the bigger the problem. A web of continuations and TCP connections, all sitting in memory, all waiting, and all posing daunting questions. What happens if the caller fails while waiting on the callee? What happens if the callee fails while being waited on? What happens if none of them fails, but the TCP connection resets? Now, the authors of Characterizing Microservice Dependency and Performances analyze over 60 million traces across 65,000 microservices at Alibaba. And their findings are revealing. Most services make no calls or only a few calls to other services. Low fan-out, shallow call depth. These services are built on synchronous remote procedure calls, so basically are built on a TCP connection. But a smaller class of services, they call hundreds of other services, high fan-out, deep call graphs. And guess what? These services are all built on message queues. So basically, the paper confirms what many engineers have already long suspected. Synchronous remote procedure calls over long-lived TCP connections don't scale. They hit a breaking point. And once you cross that threshold, you must re-architect your entire application from a simple sequential architecture to a complex event-driven one. So trading a delightful developer experience for pretty much a dreadful one. Not because you're doing something different, you're still just calling functions. Unfortunately, you just call one too many. But okay, let's do something different. Let's flip the script. Let's turn the complex into the trivial. So instead of holding on to the continuation, we ditch the continuation. We recreate the continuation only when we need to resume. So there is no longer a suspended function execution waiting to wake up. And that is a brand new execution starting from scratch. So in the paper Crash-Only Software, George Candea and Armando Fox argue that software must be well prepared for a clean shutdown as well as a crash. However, crashes are unavoidable. And we cannot just say we don't crash. So if software is crash safe, why support any non-crash safe mechanism? If you're building a crash safe system, any non-crash safe mechanism becomes unnecessary. So don't hang on to a suspended execution, to a continuation. Let it crash. No, actually, crash it. Recreate the continuation where you need it, when you need it. Okay, can we pull this off? let's explore. Let's explore this idea of resume via restart with a minimal example. So this here is clearly not distributed async await. This is also clearly not a real remote procedure call because I already hard-coded the result for it. This is only an illustration how we can implement a restart to achieve resume semantics. Right? An illustration that can be implemented in a few lines of code and that fits on a single slide. So we look at this function. And let's walk through an illustration of this function foo under resume semantics. So we start executing foo. And first, foo issues an RPC and then suspends on it. And once the result is available, we resume foo with the value 10. And now foo issues the second RPC and suspends again. And we resume it with the value 20. And then foo issues a third RPC and suspends again. And we resume with the value 30. And then finally we return the sum, which is 60. Okay. This is an entire implementation here of resume semantics in Python. It's really not like that hard. It's like run resume, takes the generator, and drives it forward, one step at a time. Basically how we assume this would work, right? Until the generator completes. So the generator object itself represents a continuation. The suspended program state that can be resumed in Python via the function send. So that's the traditional model. Keep the continuation in memory, step to the end. Or, alternatively, lose everything. The stack, the heap, the state, if the process crashes. Gone. All right. Let's walk through an illustration of foo under restart semantics. We start executing foo. And first, foo issues an RPC and suspends. But this time, we don't hold on to the continuation. We terminate it. We throw it out. Now, we execute the RPC. Once the result of the RPC is available, we restart foo with the value of the first RPC in the cache. So we start executing foo again from scratch. And once again, foo issues an RPC and tries to suspend. But since the result of the RPC is already available in the cache, we just continue foo. So next, foo issues a second RPC and suspends. But since that result of the RPC is not in the cache yet, we terminate foo once again. And we continue this cycle until foo completes, taking one additional step on every iteration. And this is a full implementation of restart mechanics. So the function run until block takes a function in the cache. It executes a function from the beginning and steps forward one yield at a time, as long as there are values in the cache. If we hit an RPC that we have not seen before, we return an object representing a suspension. Right? So the generator itself goes out of scope and is discarded. Nothing is held in memory. If we hit a return, we return an object representing a completion. Now, run replay calls run until blocked in a loop. Once again, event loop. No? And each time we get back a suspension, we perform the remote call, cache the result, and call run until blocked again. No? And every round makes a little more progress until we get back a completion. Now, this is how we turn a stateful continuation into a stateless continuation. And look at run replay. Run replay is basically a toy example, the local event loop, to our distributed event loop. What we did is we took run replay and lifted it into a distributed system. So now, finally, after all this work, we get to look at some protocols. So this diagram represents Resonate's implementation of distributed async await. The distributed event loop is divided into the Resonate server and Resonate workers. Any process that imports a Resonate SDK and connects to the Resonate server. The Resonate server acts as a control plane and is responsible to facilitate coordination and recovery, function executions, via their associated durable promises. And the Resonate workers act as a data plane. Each worker is a Python or Node.js process importing the Resonate SDK, which acts as the interface between function execution and the Resonate server. and essentially does nothing else but call run until blocked. And the Resonate SDK acts as a local event loop and interfaces with the Resonate server that is basically the global event loop. There are 3 protocols that are stacked on top of each other. They compose. There's the distributed coordination protocol, the distributed recovery protocol, and then the message passing protocol. We will start with the message passing protocol. Distributed async await is built on message passing to avoid relying on TCP connections. So there are 2 messages, unicast and anycast. So unicast, let's start with unicast, a simple one. A unicast message has exactly 1 recipient. So in this case, the message is directly sent to T1. The rest of the protocol takes care of ensuring progress even if a message is lost. So if T1 at the moment of delivery is not available, message will simply be dropped. Next, there is an anycast. A message that targets a set of potential participants but will be delivered to exactly one of them. Think of a queue in multiple consumers, or think of load balancing. And that's exactly what this does. It enables load balancing. But there is also an anycast with a preference. It's still an anycast, but now we express a preference among the eligible recipients. So here we prefer to send the message to T1. But if T1 is unavailable, we fall back to any other node of the group. Why do we do that? Well, that enables us to send a message to the optimal node. Remember that run until blocked and run replay heavily benefits from filled caches. Right? So therefore, now we can address a message to the node where we suspect that it has the most up-to-date cache, but we don't actually depend on its availability. Now, the distributed coordination part is handled by Resonate's distributed coordination protocol. And so when the caller invokes a function remotely, the SDK creates a durable promise on the server. And then the server anycasts an invoke message to a Resonate worker. And when a worker receives the invoke message, the callee starts execution. When the caller awaits the promise, just like in async await JavaScript, the SDK registers a callback with that promise on the server. Eventually, the callee terminates and completes the promise. So then the server executes the callback or schedules the callback. It anycasts a resume message back to the caller. So the caller is a preference. And finally, then the caller resumes execution. So the distributed coordination protocol is based on exactly 2 server-sent messages, invoke and a resume. It's these 2 messages, all that we need to implement coordination of executions across machines. Now, distributed recovery is handled by the Resonate distributed recovery protocol. So here the distributed recovery protocol, there's 3 components. There's a Resonate server, pluggable transport, and a worker. The Resonate server sends 2 types of messages, right? It sends invoke and resume. But these messages, they are delivered and processed in the context of a task. So the process begins when the Resonate server sends a task claim URL to a worker via some transport, HTTP or message queues. And upon receiving that claim URL, the worker proceeds to claim the task. Claiming the task initiates a heartbeat protocol between the worker and the Resonate server. And if the worker fails to send timely heartbeats, the server presumes the node has failed. So at that point, then the server reschedules the task, ensuring recovery in the case of partial failure. Then when the worker successfully completes the task, the node sends a completion request back to the server. And upon receiving this, the server marks the task as finished, guaranteeing that the task will not be retried. Okay, let's look at this a little bit more graphically. Let's walk through the life of an execution. So we trace one execution from the moment of its invocation, making a remote procedure call, suspension, resumption, and completion. This example represents the entirety of the system behavior. Everything else is just more of the same. Remember, functions compose recursively. So do these flows. More invocations, more suspensions, more resumptions, more completions. However, in this example here, we will ignore the distributed recovery protocol because wrapping everything in a task and then in a step-by-step walkthrough gets a bit boring. So we only look at the invocations and resumptions. Once you understand that, you understand everything else. So we are going to execute the function foo. It's once again foo and bar. I am sorry, didn't come up with better examples. So foo issues a remote function invocation of bar, awaits bar, or more precisely, the promise representing bar, and then returns bar's return value. So foo captures the full life cycle of a distributed async execution: invocation, suspension, resumption, completion. So we start in the initial state, no promises, no executions. And as a prerequisite, foo and bar must obviously deploy to the workers and registered with the Resonate SDK but the SDK cannot invoke what's not there. So now we start an execution of foo and we give it an ID creatively named foo1. So we can do this either with the Resonate SDK, the Resonate API, or the CLI. Here I'm showing the SDK. So when we invoke foo with the ID foo1, the Resonate server creates a durable promise representing that execution. At this point, no code is running, right? But the system knows what must run. That is how we get completion guarantees. From this point on, the system will keep trying, again and again if needed, until this execution either completes or ultimately fails, for example, because of exceeding the retry budget. Now, the Resonate server, the global event loop, sends an invocation message to a Resonate worker, the local event loop. And in this case, worker 1 picks it up. Now, intent turns into action. In response to invoke, the local event loop executes run until blocked with function foo, collecting all remote function invocations until foo hits its first suspension point. And in this case, waiting on the result of bar. So now the local event loop has determined what must be added to the global event loop to ensure progress. The request to create a new promise representing the intent to invoke bar, 1. And the request to register a callback representing the intent to resume foo when the promise representing bar completes. So the promise for bar has been assigned ID foo1.1. And again, this ID wasn't randomly assigned, but deterministically generated by the SDK during foo's execution. So it doesn't get confused on retries. Same code, same execution, same ID, every time. And once again, the system follows the same rhythm. The Resonate server, the global event loop, sends an invocation message to a Resonate worker, a local event loop. In this case, worker 2. It's like before. It's always the same beat. The local event loop executes run until blocked with function bar. However, bar doesn't suspend. Bar just completes. And now the local event loop has determined what must be added to the global event loop to ensure progress. The request to resolve the promise foo1.1 representing bar. So now the promise foo1.1 is resolved and the value for this promise is durably recorded. So only one step remains, processing the callback. Now the global event loop sends a resume message to the local event loop. And in this case, again, picked up by worker 1. And in response to resume, the local event loop does actually the same thing as in response to invoke. It just executes run until blocked with foo again. And this time bar has already been executed, so there is no suspension point. And therefore foo just completes. And now finally the local event loop has determined what must be added to the global event loop to ensure progress, and that is the request to resolve foo1 representing foo. And then the promise foo1 is resolved, the value is durably recorded, and foo is completed. No stacks, no heaps, and most importantly, No TCP connections. So distributed async await and the distributed event loop is not proprietary. They are based on like open specifications. So if you're interested to check out or contribute to the specification, please visit distributed-async-await.io. And then, okay, what can you build with distributed async await? Can you really solve complex problems with simple code? Well, my favorite answer to that question is a little pet project of mine, a deep research agent powered by Resonate and OpenAI. The agent is capable of invoking itself recursively, scheduling itself across the available nodes in your cluster. If you make additional tools available, such as executing a data pipeline to generate a report on demand, any agent can just start a pipeline run, await the result for seconds, minutes, or hours, and then just continue the rest of the computation without ever missing a beat, even on serverless infrastructure. And all that in less than 100 lines of Python code. So we released the first stable version of distributed async await this June 2025, exactly 2 years after we embarked on this journey. So currently, distributed async await is available for the Python as a Python SDK, and we just started working on a TypeScript SDK. So if you want to check out distributed async await, visit our website at resonate.hq.io. If you have any questions, comments, feedback, or you want to get involved, then please join our community at resonate.hq.io/discord. If you are interested on how we ensure the correctness of our implementation, even in the face of concurrency and distribution, then catch up my upcoming P99 Conf presentation, Squashing the Heisenberg, a look at our implementation of deterministic simulation testing in our Python SDK. And with that, thank you very much for your attention. I hope you enjoyed the last 45 minutes. And don't forget, to survive distributed systems, always double tap. Thank you.